specifically about the BDK chain traits and its maze. So, out of curiosity, who has heard about BDK? And who has used BDK? Awesome. And who has used BDK 1.0? Kind of. No, it's not. It's an alpha. We're still working on it. Cool. Thank you. So I'm going to skip this. Basically, I'm pretty new to Bitcoin. But then I started working on my own little library. They use BDK. And eventually I started contributing BDK. And now I'm full-time BDK. So today's agenda. So I'll talk about briefly what is BDK, what is a wallet library, what does it do, and some design goals about BDK chain and the specific traits. In fact, BDK is quite modular. It's split across multiple modules. And it's some very nice properties about BDK chain. And I think there's some very nice design principles that can be reused, even if you don't use BDK. I think some very nice design decisions that we made. I think is very good principle. So BDK is a library written in Rust. It's a very safe language, very memory safe. And BDK is built from the also Rust Bitcoin ecosystem. Things like Rust Bitcoin itself, like different Bitcoin structures, and also Rust miniscript. And in fact, BDK has very good support for miniscript. But when we talk about BDK, because most of the heavy lifting of the script work is already done by Rust miniscript. So when we talk about BDK, it's I'll just say that. Cool. So all the functionality. First, you manage keychains. So these are chains of script buckets we derive of a wallet script. For example, a mini script. And then you track these script buckets. And from these script buckets you track, you monitor the blockchain, you download relevant transactions to the wallet. And then from there, you build transactions. So this is the basic functionality of what a Bitcoin wallet should do. And another cool thing is it's cross-platform. So BDK is very modular. We split things up into different components. So then you use what you need to use. So the first thing is BDK chain. This is our core structures for indexing and downloading blockchain data. So basically transactions. Now we extrapolate from the data you get the UTXOC that's relevant to BDK wallet. So BDK chain is a bit more loading. But if you want something easy to use, you would use BDK wallet. And BDK wallet is built on BDK chain. And BDK coin selection is very cool. It's just purely coin selection. There's zero dependencies. There's even no dependencies to Rust Bitcoin. Now what this means is you can use BDK coin select for all different Rust Bitcoin versions. And then the chain sources. So this is where BDK chain, BDK wallet gets the wallet data from. So we have script puppy based chain sources, where these are APIs we give them the script puppy, we give the address, and they receive back the history of transactions based on the script puppy. So transactions that send and receive to the script puppy or addresses. And also we have block by block chain sources. So for example, you might run your bitcoind node on the computer, and then use the bitcoind client to emit blocks, and then BDK chain or BDK wallet just absorb the blocks coming in. It'll filter out the relevant transaction and save it in the wallet. And yeah, it's the basic overview of the BDK traits. So design goals of the BDK chain. So this is the core level library of indexing and dealing with blockchain data. are going to use it. So it needs to be hard to swap. And then it cannot have invalid representation. So an example of invalid representation is when you request a history of transactions and it returns back two transactions that you're flipping. And that's dangerous because, for example, if you're creating a transaction from there, you might have two UTXOs that will not exist together on chain. And you create a transaction which is invalid. It also needs to be modular and extendable. Modular so that people can take out what they need. They don't need to use the whole thing when creating their projects. Extendable because they want to add stuff. And then I think the last one is self-explanatory. So ambiguous representation is bad. So talk about this. So an example of ambiguous representation is in fact the Electrum API. So Electrum is based on a JSON reference and is a method called getHistory. It's a very useful method. So you give it a hash of the script IP and it returns back the transaction hash and a height. But the height is ambiguous because Bitcoin is an open network, you might have reorgs. So there might be heights where the block hash is completely different. So why is this bad? Because reals have the same height, different hashes. And wallets track multiple script puppies. And many wallets use this endpoint. So you'll request script puppies one by one. Because in a keychain you have multiple script in a keychain based on what the script does, you have multiple script puppies. And request these script puppies one by one at different times, non-atomically. And get histories where these transactions have different types. But sometimes we might have confidence because of the reorgs that are happening. Another example is if, for example, you want to connect to multiple Electrum nodes and you send your script pubkeys to these different Electrum node histories. And the same problem arises because different nodes might have different views on the network. They have different tip hashes that are conflicting. And then again, your wallet will have the history of transactions, which is ambiguous. So the BDK, we don't want to incentivize this. This is a bad API, it's dangerous. So BDK, you need to anchor a transaction to a block height and a block hash. So we identify blocks in BDK by block ID, height and hash. Technically we could do just hash, but I think with the height it just becomes a bit more convenient. Sorry. So this is a trait in BDK. It's called an anchor. So I think with traits, this it's like a loose bound on every different type. So you can implement your own type here to use your wallet. So this is where the extendability of BDK comes in. What this basically means is you can associate multiple anchors for transaction ID. And basically what it says is as long as the anchor block is the best trader, the transaction associated with the anchor is guaranteed to be the best trader. I think a very good design philosophy when designing these anchors is you need enough for it to be correct, but you need to set these like setting the bound of how it's defined. So it needs to be loose enough to allow for flexibility of the port. So in summary, Electrum's getHistory endpoint returns only confirmation height for transaction that's ambiguous and dangerous. You might have inconsistent history. And BDK requires transactions to be anchored to block height and hash. Now the question is, does it mean that BDK compatible with receiving data from Electrum? The answer is no. So BDK is split into multiple grades. You have the BDK chain, and you have chain sources. Example is BDK Electrum. And this is how we deal with this situation of the ambiguous types. So how it works is first, the BDK Electrum grade grabs the chain before pulling the history for each strip up here. And after you get your history of transactions, you check that the chain tip at the end of this thing is the same. So if the chain tip is the same, you assume that it's more than no rewards. And that means you can create anchors anchoring all the transactions to the tip.
It's very good if we could.
The first approach is technically there's a possibility for multiple rewards during your set. So maybe the chain that you start off with gets rewarded down but reintroduced later. I mean, the chances of that is very low. But the fact that it has, it's very slow, but the chance that it can still happen is just not very nice to think about. So an alternative approach is we use the other methods of Electrum, so such as transaction get verbal against every transaction. And then we can create a custom anchor type for it. So you have custom anchor types that have like a whole verbal proof linking it to the block that is anchored. It's very nice. Or you can just have like the position of the transaction. So now we talked about how BDK incentivizes non-ambiguous data structures. And now we'll talk about monotone data structures. So what do we mean by monotone? So basically, it's a data structure where updates, well, the way we describe it, it's a data structure where you can update it and apply these updates in any order, and the final result will always be the same. So theoretically, so there's no such thing as invalid representation. And it will be very equal async. So async is when, because the nature of networks is when you send a request, you don't know when you get a response, you don't know when you'll receive a response. And for example, if you're connecting to multiple Electrum nodes, you don't know when things are coming, so it'll be good to have a data structure where it doesn't matter in what order you receive the updates. Yeah, so that's why monotone structures are very nice. And an example of a monotone data structure is called the transaction graph. It's basically a fancy set of transactions plus some metadata. So there's only two types of metadata in addition to the transaction on the graph. It's anchors, which we just talked about. Anchors basically say that if that block is in the chain, then our transaction is in the chain. And also we have this last seen. It means last seen in the network. And another part about transaction graphs is we index spends. So for example, this out point is spent by these transactions. And you're allowed to have conflicting transactions in the transaction graph. And as you can see, these pieces of data is true even in itself. Transactions are always transactions. Anchors are always valid because of blockage, because of nature of hashes. So a transaction exists under certain block, exists under certain block. So you can receive this set of information asynchronously in any order will be okay. So this is the internal structure of transaction graph. So transactions, we have text node internal because we want to have allow for partial transactions. So something you don't have the whole transactions, you just want to sort out points of the transaction. And then we do set off anchors as a generic, and then then the last thing timestamp, and everything else is just indexed backwards and so how do you use transaction graph? So one of the guarantees that BDK has is you can always extrapolate a consistent history of transactions. So again, consistent history means a history where there's no conflicting transactions. Or no two transactions that split the same output. And to do this with only having transaction graph is not enough. The anchors, you know that the flat block is this, in this transaction exists in this chain, but we don't know which block hashes are in this chain. So the missing component now is this. So this is where another structure comes. This is the chain oracle. So basically, method is block and chain. All chains are identified by the chain tip, and there's a block ID, which is just the block hash of block ID. So you can call this against all the anchors in the chain. The anchor, this is the chain, it's a transaction chain. And then the get chain tip is for convenience. So for example, if you are syncing from bitcoindev, you can implement the chain oracle on top of the bitcoindev client. But we also have a local representation where you grab updates from Ultra or Explorer and you create a local chain oracle that's for local. So putting it all together, you can, this is a visual transaction graph. It's called this chain transaction. It takes in the chain oracle and the chain tip, and it returns the consistent history of transactions. How does it work? So for each transaction, we check whether one of the transactions anchors to a block chain. And if it does, that means the transaction is confirmed. Because it's in the blockchain, you can see it's confirmed. So it's part of the history. And then the next part is to deal with unconfirmed transactions. So the transaction conflicts with the confirmed transaction. So the unconfirmed transaction conflicts with the confirmed transaction. That means that unconfirmed transaction can't exist in the same chain. Third point is dealing with two different unconfirmed transactions. We prioritize the one that's last seen. So we basically assume that if we see it later or closer to, we see the transaction on Mutable more recently, we'll assume that one exists in the Mutable. It's not perfect, and we private by a transaction ID. So the problem with this is the performance is not great. So right now with most wallets, it's not really transactional wallet. Like iterating through all the transactions and comparing with other transactions to confidence. So like the O notation will be quadratic. So like m squared. Yes. Yeah.
So the TM that you're looking at, is that itself unconfirmed?
Yeah, so the last one is the transaction we're looking at is unconfirmed.
So, and you're comparing it with another unconfirmed.
Correct.
So you're saying prefer it if it's the last seen back in the other words, if it's more recent.
Correct. It was more recently seen in the middle.
So that's, so there's an RDF. What about the RDF? It's not really, that isn't really how the system works.
I'm sorry?
You're saying that you're assuming it is a replacement and it is going to replace that. What's the thinking behind that reference?
Right. So,
Your RDF is
Yeah, it knows RPM because we can't. Yeah, so because like right now there's like package relay and things like that. We might not have. So to be fair, it might not be the best way of doing things, but I think it works right now. Because yeah, I mean this is the point that can it can be better, I think. But I think right now it's a pretty good assumption.
But that's what I'm trying to get at. So you think that's a pretty good assumption because replacing the
Yeah. Yeah.
because now there's you got all the
The power of it, yeah.
Yeah, I'm not going to show it's like very hard to
Yeah, I mean, honestly, like, if someone has a better idea, I'm all for it. But, thank you for bringing it up. Yeah, so right now it's not great. It's quadratic. On the out pipe. The solution is you traverse the graph via the spins. It's not done. If someone works on this, it'll be awesome. So you start with the root, the earliest transactions, and you just move through the graph. Because you get to a point you complete all the conflicting transactions. You go through it once and then it's over again, which is very nice. That's not done. Someone can do it, that'll be nice. Am I out of time? Should I just continue? Yeah. So recap transaction, graph the seal transactions, and you also put metadata, anchors and timestamps. Anchors anchor to the chain. Timestamps is what you use to compare different transactions. Transaction is monotone, updates can be put in any order. It's very nice to work with, especially in async. And then the chain oracle brings everything together. So we can extrapolate a consistent history. This is the first meme that BDK is not very good. It's just things pointing with each other. It's a good representation of what's happening on chain. And then another question is how do we get the relevant UTXO set? Because we talked about transactions, but we can't really talk about UTXOs. So just with an index of margin. I'm really worried about time.
It's only a break off.
Okay, cool.
Just keep going to somebody. It's a break, no, it's a break. It's a coffee break, it's fine.
Okay. Cool. Thanks for support. So, there's another trait. A cool property about BDK, or every structured BDK, we have something called change sets. So, it's quite open-ended. So, what it means is change set is what is persistent. So, you have the structure, you apply updates to the structure, and any updates that anything that changes in the structure is submitted as a change set, and you just persist the change set. So you get so all structures have this. We have a transaction graph, we have it in our local chain oracle, and then we also have it for our indexer implementations as well. So that's besides the point of what the indexer does. So the indexer just indexes transactions. That's all it does. It's just you give it a transaction and it indexes it, and that's it. And then there's another method called this transaction development. So for example, this is good for white boxing because you only want to download or store the transactions that are relevant to you. So over here you can iterate over all the transactions in the block and just pick out what's relevant for that. I haven't gone to the bridging yet. So keychain DXL index, indexer. So keychain DXL index, it keeps trace of strip keys for keychains. So in this case, the keychain is like the descriptor, and then a mini descriptor, and you can derive multiple descriptors from. And then it scans the transactions with the method of the train. And then it stores the out points that contains track strip buckets. So to recap, keychain takes out, it keeps keychains, chains of strip buckets, it caches it, and it scans transactions and compares it against the strip buckets. And then it stores, indexes and stores the out points that are relevant. So now we have structure put against the transaction graph, the chain oracle, where we can get a list of spare transaction. And this is how it works. So the chain tip identifies the blockchain. The outpoints, we get the outpoints all from the indexer, it's the index. And then we have this. So right now this is on the machine. We could do something similar to what I talked about in terms of the other methods to get consistent real transactions. So this most of these optimizing, but right now we're focused on API first. We do optimizations later. There's plenty of work to be done. So summary, we have the transaction graph. It's a set of transactions and some metadata, such as anchors, which anchors the transactions to the chain, and also the last seen timestamp. We have the chain oracle that tells us what blocks are in the best chain, and we have the indexer. You can do really cool things with the indexer. So for example, right now we have keychain index on the index, but in the future, for example, silent payments. I think the structure here could do a very nice silent payments implementation of really indexer. So it's quite flexible. And these structures are nice because they monochrome. And then also it's not ambiguous. And again, you always guarantee to get a consistent view of transactions and you think so. As long as the block source is reliable. This is like it's much extendable because of the traits. Questions? Thank you. Yes.
So going back to TX graph, would it be possible to store the transaction fee amount in the graph and then use that as your precedent?
So right now we actually don't explicitly store the transaction fee. So that means we need to derive it from like the previous outputs. So that's why we allow storing floating outputs. So it's expected, but basically transaction to transaction graph is for like transaction internal. It can either be a full transaction or have a transaction with just certain outputs that you care about, which help you extrapolate the thing. That's part of the design.
Okay, another question.
Yeah.
So I see BDK doesn't want to store the entire blockchain too much data.
Yeah.
So is there any other ideas on the horizon as far as condensing blockchain data and maybe virtualizing the UTXO set?
You mean like the UTXO set? There's the UTXO project. I'm not working on it, but in fact, the core implementation of UTXO, which is UTXO-D, recently there's a PR with integrated BDK into it. Yeah. Yeah.
Have knowledge of the entire UTXO set and sort of 3XO
Sorry, I missed that question. So, BDK has knowledge of the whole UTXO set?
Yeah, in the style of like a virtualized
Right. So how BDK works in UTXO-D, it's not perfect. So in UTXO-D, you have to have, because it's basically the UTXO set becomes. I'm not expert on UTXO-D, but basically you have to aggregate Merkle tree on utixos, and then when you spend the transaction, you want to prove that your utixos belong in that Merkle tree. Right now, the implementation with BDK doesn't store that data, but in the future is something that we want to store properly. Right now, we're relying on something in the Utrix-OD network called like bridge nodes. That's bridging Utrix-OD nodes with the rest of the network to work with the BDK wallet. But in the future, I do want to work on having BDK support Utrix like natively. I think that would be really cool. Yeah. And please, if you're interested in our project, please put us on Discord.